it helps to reduce the time on computation. Then the filter shape is 3 by 3, 3264, the output, and then this is the input. Then we keep the same stride to preserve the special. We keep the same stride shape 111, and then for padding we keep the same padding same in order to preserve all the special dimension in our image. Also, we use a ReLU activation function, and this for the ReLU layer, no need to do anything, just process the data, no need to extract any features. And then we use the pooling layer. The method we use is a mass pooling method. Also here we use a 2 by 2 window size or the corner size. And here we use the window shape 1, 2, 2, 1. Here for this one we use stride 2. Means for the pooling layer, enable the filter to move 2 pixels each time. And here we also keep the same padding. The input is 64, input channel 64, and then here is input shape, and this is the input and the output also 64. And here is flattened. The image is flattened, ready to be introduced into the fully connected convolutional neural layers. Here, this the shape of the flattened shape for the fully connected layers. And here the fully connected layers with the dimensions 8 by 8 by 64, and the output channel is the input channel. And then for the second fully connected layer, it has a dropout layer, and it has a dropout layer. And the dropout layer helps to learn more diverse features without relying on any specific input feature. Third and the final fully connected layer is the output layer. Output layer, this acts as a classifier to map and output the final features into 10 different classes based on this one hot for this image is about we have 10 different classes. So here is the output channel for this, which is 10 for these 10 classes. And here is the image of the diagram or the architecture of what I just explained now. Here is the input 32 by 32 with the color, which is 3, and then it will go into the convolution layer, and then the convolution layer is a 3 by 3. Then the ReLU is applied, and then to pooling layer, and then the same process until it gets to the flattening, where the image is now resized, flattened to be moved into the final convolutional fully connected layer, which will output the different classes. This is the example of like for one hot encoding. One example is at the index of 0, when is 1, other classes will remain 0. If one index 0 is 1, other classes will remain 0. That's the one hot encoding. And here is the result of our first testing on CIFA 10 model. Here you can see from the training at the beginning, the first step at the step 0, the accuracy was just below around 10.61, which shows that the image has not been trained yet. So then at step 100, it shows that the image is already learning, the layer is already learning some features. And as you can see, this follow the gradual process until it gets to the final step of about 4,000, 5,000, because this index starts at 0 instead of starting 1. So this is the final step, and the accuracy we got for this image, for this CNN on this CIFA 10 model is 70.74. For this, the result in the table shows that the performance or the accuracy of our convolutional neural network model with 2 convolutional layers at various steps. The CIFAR 10 has 10 classes, and the model classified the images into 10 different classes based on the training. And each line in these data sets represent the step. And our step is 100. Each is 100 in batch. Batch step is 100. As you can see, 0, 100, 200. And then this is just the description of what I just explained. Here, the model accuracy was very low at the initial stage because the model then is performing poorly because it has not been trained yet. So it was making random prediction. And as the training started, you can see the model started to improve significantly. At step 100, it jumped to 42.22%. The accuracy continued to improve, and the data sets continue to be and then the accuracy continued to improve as the model experienced more minor fluctuations in accuracy throughout the training. As you can see, it goes up and it goes down. Here it was 61, and then 68, 69, until we got to the final about 70.74. Here it was 71, and it went down to 70.74. So the accuracy continued to improve until the final step. Then the parts, on these parts, we compare the 2 different convolutional neural network performance based on the MNext data sets. And as you can see, this is a grayscale data set, and this is our CIFAR color image. Here, they both started at a very poor or at a very low rate because the training has not, they've not started learning at the beginning. But as you can see, the grayscale, the next step was 100, and it jumped to 95%, and this one was 42. From here, you can see that the grayscale has a high rate of learning because the dimensions are much more smaller, and then it requires less computation power, more than the color image. And the final step for this is 99.14%. For this one, it was 70.74% for our color image. And this shows a high rate of convergence, more than the color image. And then we compared our analysis on the different models, the MNIST and the CIFA-10 model, and you can see the accuracy level of the both data sets at different steps. Each line in our data set, each line in our training represents a step of 100 batch step, and then the accuracy was about 10.61 for CIFA, and then at the beginning at step 0, and then it was 13.66 for MNIST, which show both model has not been trained yet because it has low accuracy at the beginning. And then this the accuracy improved significantly to 95.02 for MNIST and 42 for CIFA. Although the higher rates of increase in MNIST dataset shows that the learning process and computation rate is faster in grayscale images than the color images of CIFA-10. The accuracy continued to improve for both models, then until we got to the final accuracy. Then here the model reached the final accuracy of 99.14 for the MNIST and then 70.74 for the CIFA-10, showing that the both models have converged very well, and then they've been